June 2017. Let's have a look now at question number 1. So we've got a Maxwell-Boltzmann distribution curve of molecular energies. So we've got energy along the bottom and number of molecules up the side. Just to note the shape of the curve then, no molecules have no energy at all. So here it goes to the origin. This energy here coming down and touch it, and if you go down from the peak down here, is the energy that most particles have. The average energy will be just to the right. And then if you note that the line never touches the x-axis. It doesn't touch the x-axis because there's always some molecules that have a very high energy here. So let's have a look. Label the horizontal axis, that's energy. Draw a distribution of molecular energies at a higher temperature. So at a higher temperature, the whole of the curve shifts to the right hand side because the particles get a higher energy on the whole. The peak, however, goes lower because the area underneath the curve represents the total number of molecules, and that needs to stay the same. So the curve is going to shift to the right, and at the end here it ends up higher because more particles have a very high energy, then the peak needs to lower as well. So it will look something like that. The gas decomposed on heating. Explain why an increase in temperature increases the rate at which this gas decomposes, because as you increase the temperature, then more particles have more energy, and more particles therefore have the required energy, which is called the activation energy. Let's look at question number 2. So we've got a volatile hydrocarbon. Volatile means it's got a low boiling point. Hydrocarbon means it contains hydrogen and carbon only. And we seem to have been given the mass of it, the temperature of the system, of the room, the pressure and the volume. So it's pointing towards PV equals nRT, especially since we've been given R here as well. So the only equation with R in it is PV equals nRT. So that's clearly what we've got to use. Remember, temperature is going to be in Kelvin, which is correct. If it weren't in Kelvin, if it were in degrees C, to convert degrees C into Kelvin, you add 273, but it's already in Kelvin. Pressure has got to be in pascals. It's in kilopascals, so to convert a large unit like a kilopascal into a smaller unit like a pascal, you multiply by 1,000, so that's 102,000 pascals. Centimetre cubed is actually going to be in meters cubed, so to convert centimetres cubed into the next unit up, which is decimetre cubed, you divide by 1,000, and to convert decimetre cubed up into meters cubed, you divide by 1,000 again. So it's actually going to be divided by 1,000 divided by 1,000 to get into meters cubed. Let's have a look at our equation then. PV equals nRT. P is in pascals, 102 kilopascals, 102,000 pascals, so we've converted that. Volume is in meters cubed, so as we said, 72 centimetre cubed, divide by 1,000 to get into decimetre cubed, divide by 1,000 again to get it into meters cubed. Temperature is already in Kelvin, so let's put these numbers in then. Pressure 102,000, V 0.00072 meters cubed. N is the number of moles, which I think we've got to find out. 8.31 is the gas constant, R, and temperature is temperature in Kelvin 373. So if we multiply these two out, always good to multiply out the numbers first on a calculator so you don't end up pressing the wrong buttons. 102,000 multiplied by 0.00072 is 7.344. So do that section first and multiply these two numbers, 8.31 and 373 out, and you get 2738.6. Now n is 7.344 divided by 2738.6, and it comes out as 0.00268 moles. I've now got the number of moles. What else do I know about x? I know the number of grams, or at least I can do 194 milligrams. To convert a smaller unit into a larger unit like a gram, because it needs to be in grams, divide by 1,000, 0.194 grams. So now what have I got? I've got moles, I've got mass in grams. I can work out the MR because moles is mass in grams divided by MR. So 0.00268, which is the number of moles, is 0.194 grams divided by MR. Rearrange the equation so that MR equals 0.194 divided by 0.00262, and it comes out as 72.4. Let's have a look at how many significant figures. Most of them these seem to be to 3 significant figures: 194,372, 102,000 to 3 significant figures, 8.31 to 3 significant figures. So we'll put it to 3 significant figures because most of the others seem to be to 3 significant figures. 72.4 to 3 significant figures. Analysis of a different hydrocarbon Y shows that it contains 83.7% mass of carbon. If it's a hydrocarbon, it only contains hydrogen and carbon, so there's 83.7% of carbon. The remainder must be hydrogen. So if you do 100 take away 83.7, you'll come out with 16.3% is hydrogen. Let's have a look at the solution then now. So we've got 16.3% is hydrogen, 83.7% is carbon. You divide by the atomic mass of each of them. The mass of carbon is 12, the mass of hydrogen is 1. So if you divide each of those, 83.7 divided by 12, 6.975, and this one turns out as 16.3. Not a great ratio, that. So you divide by the smallest, 6.975, 16.3, you divide both of them by the smallest number, so that equals 1. 16.3 divided by 6.975 equals 2.33. So the ratio is 1 to 2.33. Then you multiply by a number you're going to have to spot the number that you need to multiply by to get this fraction into a whole number. 2.33, if you multiply by 3, that equals 7. And this one equals 3. So multiply both of them by 3 and it ends up as a ratio of 3 to 7. So its simplest formula, its empirical formula, is C3H7. Now it needs us to work out, after the empirical formula, the molecular formula. So the molecular formula is its true formula. So we get this from the MR. So we look at the MR. If we add up C3H7, a carbon has got a mass of 12, so that's 36. A hydrogen has got a mass of 1, so that's 7. 36 add 7 is 43. That seems to be half 86. So the true formula is going to be double this, C6H14. You can check out his MR then equals 86 if you wish. Question 3, let's have a look. Let's have a look through it and read through it before we do spoilers. Compounds A, B and C all have the molecular formula C5H10. So C5H10, if you double the 5 and it ends up as a 10, it's got the general formula CnH2n. So it looks on first impressions of it's an alkene. With a double bond. A and B decolorise bromine water, so A and B do have a double bond, but C does not. So that's strange. C5H10, the general formula of an alkene, double the number of carbons, end up with a number of hydrogens, CnH2n, but it hasn't got a double bond. That shows that that can happen if it's cyclic. If it's got a circle, it can have single bonds, but the general formula of an alkene. So C is definitely cyclic, and that will explain why it doesn't decolorise bromine water, but it can have CnH2n as its general formula. B exists as 2 stereoisomers, but A does not show stereoisomerism. So the double bond. Stereoisomers are geometric isomers at AS level. So geometric isomers means that there's a double bond in there, and the double bond has no free rotation. So what that means is that stereoisomers can have the same structural formula but different positions of atoms in space. And B has got geometrical isomerism, so it means to the left of the double bond 2 of the groups are different, and to the right of the double bond 2 groups are different. A has a double bond but does not show stereoisomerism, does not show geometrical isomerism, and so to the left of the double bond 2 of the groups must be the same, or to the right of the double bond 2 of the groups must be the same. Let's have a look then at the solution. A and B are unsaturated, have a double bond. Yes, we established that. B has 2 different groups to each side of the double bond. Could be pent-2ene. Pent-2ene, yes. We've drawn actually Z-pent-2ene here. That's fine. Let's just check out that it does have the properties that it describes in the question. Does it have a double bond? Yes, it does. It will decolorise bromine water. Does it have 2 different groups to the left of on the carbon to the left of the double bond? Yes, it has a H and a methyl group. Those 2 are different. Let's check to the right. A H and an ethyl group. Yes, those 2 are different. It will show stereoisomerism or geometrical isomerism. So let's just check out whether it's Z or E that I've actually drawn. So if I go to the left of the double bond and find the carbon there, it's joined to an H and it's joined to a C. So the H has the lower atomic number. H has an atomic number of 1, carbon has an atomic number of 6, so this group would take priority. You'd highlight that. To the right of the double bond, hydrogen has an atomic number of 1, carbon has an atomic number of 6, so I'd highlight this one here as taking priority. Both groups on the same side, that would be Z pent2E. Let's now have a look at A. A has two groups on the same side of the double bond which are the same, so it could be something like pent1E. Let's have a look here. The carbon to the left of the double bond, yes indeed, does have two hydrogens, two groups that are the same, so it's not going to show stereoisomerism, it's not going to show geometrical isomerism, even though it will decolorise bromine water because it's got a double bond. Let's have a look then at C. C we said is saturated. It's only got single bonds because it doesn't decolorise bromine water. Yet it's got the formula of C5H10, the general formula CnH2n of an alkene. So that means that it's cyclic. It could be something like cyclopentane. Single bonds, C5H10. And the definition then of a stereoisomer, a geometrical isomer, is that they have the same structural formula but different positions of atoms in space. Question number 4. When an alkane is burned in excess, that means a plentiful supply of oxygen, they produce carbon dioxide and water. So while there's an excess, lots of, a plentiful supply of oxygen, it's called complete combustion, and carbon dioxide and water is made. Incidentally, if there isn't an excess of oxygen, or not a plentiful supply of oxygen, not enough oxygen, it produces carbon monoxide and water, like there is in a faulty gas boiler where there's not enough ventilation oxygen coming in. It can also make a black solid like it does coming out of a car exhaust engine, called carbon as well, if there's not a plentiful supply of oxygen. Anyway, there's an excess, a plentiful supply of oxygen, so it's going to make carbon dioxide and water. Complete combustion rather than incomplete combustion. Complete combustion, making carbon dioxide and water. Propane. What's propane? C3H8. It's got single bonds, so the general formula CnH2n plus 2. 3 carbons in propane. Double it, add 2 is C3H8. Reacting with oxygen, we'll come to the 5 in a minute. It makes carbon dioxide and water. We'll come to the 3 and 4 in a minute. So I've got C3H8 plus O2 making 3 CO2 and 4 H2O. The only place that the carbons can go is into the carbon dioxide, so 3 carbons must be 3 CO2. The only place the H's can go is into the water, so 8 H's must be 4 H2O to make 8 H's on either side. And now we can balance the oxygens. Let's work out how many oxygens we've made. 3 times 2 is 6. 4 times 1 is 4, 6 add 4 is 10, a number multiplied by 2 to equal 10 is a 5. Question 4.2 is a little bit of maths. It says we've got bond enthalpy data and we've got an expression for the bond enthalpy is minus, and then in brackets 496N plus 2O2. That's an expression for the bond enthalpy, and the bond enthalpy of combustion is minus 6650. In other words, this expression equals minus 6650, and you need to solve it for n to work out how many carbons there are. N carbons, we've got to work out n. So let's have a look at this. Enthalpy of combustion equals minus 6650, and it equals this expression, minus 496 plus 202. You may know from maths that if there's a bracket, then everything, the minus applies to everything throughout the bracket. So minus 6650 equals minus 496, and that's a plus, but it gets a minus 202. Now what I'm going to do is I'm going to rearrange. If you look at how I've rearranged, I've taken the minus 469n across the other side of the equals sign, so a minus then becomes a plus, so it's 496n, and I've taken the minus 6650 across to the right hand side of the equals sign, and that becomes then a minus becomes a plus, so it's minus 202 that stayed where it is, and a plus 6650 gone across to the right. So 496n, let's do this little calculation first, equals 6650 take away 202, which is 6448. divide both sides by 496, so N equals 6448 divided by 496, it equals 13. So I've got 13 carbons. I know the general formula for an alkane is CnH2n plus 2, so I double the 13 to 26, add 2 and it becomes 28. Its empirical formula is C13H28, and that's probably its molecular formula as well, I would suspect. Suggests one reason other than the use of mean bond enthalpies why a value of the enthalpy of a combustion of a liquid alkane is different from the value obtained in the expression. Tricky question this. The liquid needs to be heated and turned to a gas before it will combust. This needs to be a gas, so your fuel needs to be evaporated into a gas before it will actually react with oxygen and burn. So the liquid alkane actually needs to be evaporated and turned into a gas before it'll actually burn. So there's another factor in there, that the value, which is the enthalpy of combustion, the energy that's given out when you burn it, here is not going to equal the practical value, because you've also got to evaporate it before you actually then combust it. So there's heat energy needed to turn the liquid alkane into a gas before it's combusted. A tricky question, that. Here now we've got some values, so we've got enthalpy change when you combust each of these alkanes, and we're missing a value of propane. We've got to plot this on the graph, and then we've got to use the graph to work out the value for propane. If you plot it on a graph and you put the points there, you'll get a mark for the points, and then if you put a line through it, you might be tempted to put a straight line through it as a line, draw a line of best fit. That's actually wrong. A line of best fit doesn't have to be a straight line. If you look, you get a better line of best fit by doing a curve. It can't just be zigzagged. You can't just join all of the points with a straight line. It's got to be a line of best fit, but a line of best fit could be a curve, and I think a curve fits that better. As long as it's a smooth shape, either a straight line or a curve, that can be a line of best fit. So I think your line of best fit is sort of like that, and then when you read from the graph, methane, ethane, propane, butane, pentane, 1 carbon, 2 carbons, 3 carbons in propane, 4 in butane, 5 in pentane. So we've got 3 carbons here. We go down until a line and we read it off here, and I think it's minus 51.4, something of that nature. We've got spoilers here, sorry about that. When isooctane is burnt, the enthalpy change is minus 47.8 kilojoules per gram. That means when you burn 1 gram of this isooctane, it releases, the minus means it's exothermic, gives out 47.8 kilojoules of energy, 47.8 thousand joules of energy. It's liquid at room temperature with a density of 0.692. And we've been given a volume. Why are we given density? Well, density is mass over volume. That's the only equation we know, and that must be the equation to use then if we're given density. Otherwise they wouldn't give us density. Density is mass over volume. Look at the units of density. It's in grams and it's in centimeters cubed, so the volume needs to be in centimeters cubed to match this value. I've been given 1.00 decimeter cubed, so I've got the volume, but it's in decimeter cubed, and it needs to be in centimeter cubed to match that centimeters cubed in the density value. So how do I convert 1 decimeter cubed into a smaller unit value of centimeter cubed? Then I multiply by 1,000, so 1 decimeter cubed is 1,000 centimeters cubed. So now, density is 0.692. The mass, I don't know. I'm not given the mass. I think that's what I've got to work out. Divided by the volume that needs to be in centimeters cubed to match the units of density, divided by 1,000. Mass equals 0.692 times 1,000, so I've multiplied through by 1,000. And that will equal 692 grams. And it's in grams because the units of density are in grams. So the enthalpy change now tells me that I have 692 grams. The enthalpy change is minus 478 kilojoules when I burn 1 gram per gram. So minus 478 kilojoules per gram. Gram to the minus 1 means that you're burning 1 gram. And and so for 692 grams it's going to be 692 times the value when I've burnt 1 gram. So minus 478 times 692 is 33077.6 kilojoules. The answer should be in the same number of significant figures as the other values. 1, 2, 3 figures. 0 doesn't count to the left. 692 is 3 significant figures. 1.000. I've got to try and get it to 3 significant figures. I'm never going to get this to 3 significant figures, but I need to get it to 3 numbers at least. I need to round it up. 331, 3 whole numbers, and then with 2 zeros at the end. That's the best that I can do. Ethane dioic acid is a diprotic acid. That means that 1 mole of acid reacts with 2 moles of sodium hydroxide. Sodium hydroxide is a base or an alkali. So diprotic acid, you only need 1 mole of acid to react with 2 moles of the hydroxide. Hydroxide being a base or an acid. Anyway, we've done a titration, so we've added acid to the base or the alkali, and we've measured volumes, we've got some known concentrations, we can do some calculations. So what have we got first of all? Reacted completely with 25 centimeters, 25.30 centimeters cubed of 0.5 mole dm to the minus 3 sodium hydroxide. I've got a volume and I've got a concentration of sodium hydroxide. I've got 2 values. It wants me to work out concentration and volume. Concentration is moles divided by volume in decimeter cubed. It wants me to do that calculation first of all. So let's have a look at the calculation. So for sodium hydroxide, I've got a volume 25.3 centimeters cubed. However, concentration is moles divided by volume, and the volume needs to be in decimeter cubed for concentration equals moles divided by volume. We can see the units of decimeter cubed there. So we know this centimeters cubed has got to match the decimeter cubed of the concentration. So let's change centimeters cubed into decimeter cubed. It's a small unit up into a larger unit, small unit up into a larger unit, so you divide by 1000. 25.3 divided by 1000, 0.0253 decimeter cubed. We've got the concentration already, that's fine. Concentration equals moles divided by volume in decimeter cubed. So concentration 0.500 equals number of moles divided by the volume in decimeter cubed, 0.0253. Multiply both sides by 0.253, so now you end up with moles equals 0.5 times 0.253. Number of moles of sodium hydroxide is 0.01265. Now, why have they given me an equation? What is an equation? An equation is a recipe, a chemical recipe to show me the amounts of chemicals that react together and what's made. So I've got 1 mole of the acid reacting with 2 moles of sodium hydroxide. I've got the molar ratios 1 to 2. 1 mole of this reacts with 2 moles of this. So if I've got sodium hydroxide 0.1265, 2 moles of sodium hydroxide will react with 1 mole of acid, half the amount. So if I half this amount, 0.01265 moles of sodium hydroxide, if I half it, 2 down to 1, it'll tell me the number of moles of acid that I've got. So divide by 2, I've got 0.006325 moles of acid reacting with 0.12565 of sodium hydroxide. I've now got the number of moles of acid in this 25 centimeters cubed. So the confusing thing now is that you might think, well, I've got moles of acid and I've got volume, I'll work out concentration of acid. You don't need to do that. But read the question. Calculate the mass of acid in the 25 centimeters cubed. So in this 25 centimeter cubed, I know I've got 0.006325. I've got the ethane dioic acid, so I can work out its MR. I've got moles. Moles, I can work out its MR. 2 H's are 2 1s. 2 carbons, 12 each, is 24. 4 16s are 64. I can work out that the MR of the ethane dioic acid is 90, and I've got moles, so I can work out mass. So number of moles 0.006325 in this solution, 25 centimeters cubed solution, equals the mass of the acid in there divided by its MR. So the mass equals 0.006325 multiplied by the MR 90, 0.569 grams in that 25 centimeters cubed. It wants it in milligrams. How do I convert a big unit like a gram down into a smaller unit like a milligram and multiply by 1,000 to go that way? So multiply by 1,000 equals 569. I'm not sure why there's an 8 there. 569 milligrams. The student used a wash bottle containing deionized water when approaching the end point to rinse the inside of the conical flask. Explain why this improved the accuracy of the titration. Well, it washed any of the sodium hydroxide from the side of the flask into the mixture to make sure that all the sodium hydroxide had reacted. So washing it down into the flask, make sure that there's no sodium hydroxide on the side of the flask that doesn't react. Give the meaning concordant titers. What concordant titers is, if you do titrations, they're called titers. An individual result from a titration is called a titer. Then the three, if you've got 3 or 4 or 5 or 6 or 7, however many titers you've got, how many results from your titrations, you need to choose 2 titrations which are within 0.1 centimeters cubed of each other. So you pick 2 of your titers, 2 of your results from your titration, however many you've got, and you just use those 2. And those 2 have got to be no more than 0.1 centimeters cubed away from each other, apart from each other. Those are the 2 that you use, and you ignore any of the others. That's what concordant means. 2-methyl-propan-1-ol can be prepared from reacting 1-bromo-2-methyl-propane with dilute aqueous sodium hydroxide. A mechanism for this reaction. First of all, note the word dilute aqueous. Dilute aqueous means it's got water in there. When you use cold water, it doesn't specify the condition of cold, but we know there's water in there. Cold water, what actually happens is the hydroxide group on the sodium hydroxide replaces or substitutes itself for the Br. So the Br is lost and the hydroxide replaces that. That's what happens in cold water when water is present. And therefore the Br comes off, and the Br on the 1-bromo, the bromo on carbon number 1, is replaced by an OH group. An OH group is sometimes called an ol group, and look, there it is, a 1-ol. So name the mechanism. Well, OH minus is a nucleophile. We'll discuss that in a minute. It's a nucleophile and it's swapping itself for the Br, so it's nucleophilic substitution. Let's have a look at the mechanism now, and we can understand what a nucleophile is and what's actually happening. So in cold water, sodium hydroxide dissociates. Dissociates means breaks up. It breaks up into its ions. It breaks up into Na plus ions and OH minus ions. The Na plus ion isn't important. It's a spectator ion. It just sits there and doesn't do anything. So you don't include that in the mechanism. If you do, if you include Na, sodium, Na plus in the mechanism, you will get it wrong. You only need the hydroxide part. That's the part that reacts. And a hydroxide ion is an OH minus ion, but it's got a lone pair of electrons on the O. Remember, a curly arrow can't come from a minus. It can only come from a double bond, a single bond, or a lone pair of electrons. So a lone pair of electrons is important. Do not include the Na in here. And what it's going to do is it's going to substitute itself for the Br, and the OH is going to join on, and the Br will be lost as Br minus. Let's have a look at that in a little bit more depth. Now, this is a polar bond. C to Br is a polar bond. What that means is the Br is electronegative. It withdraws the electrons along that bond towards itself. That's what electronegativity means. And in doing so, the electrons, which are minus, give a very small minus charge to the Br and a very small plus charge to the C as they're drawn along here along this bond towards the Br. That gives a reason for the lone pair of electrons therefore to attack or bond with the carbon, because that's got a plus and these electrons are minuses, and they will actually form a bond then to that carbon. The lone pair of electrons, that lone pair there, are actually now in that covalent bond there in between the C and the OH. They've bonded to the carbon. The carbon can't have 5 bonds, it can't have an extra bond, so it's got to release a bond, and it breaks. The electrons go onto the Br. After all, they're being withdrawn to the Br anyway with its electronegativity, and now they go. So they go from here onto the Br. Electrons, remember, are minuses, and that's why that ends up with a Br minus over here. The OH has lost its charge because it's given electrons away, it's donated them. And that's the definition of a nucleophile. What a nucleophile is, nucleophile in Greek, nucleo means plus. It comes from the word nucleus, and nucleus has got protons in it, which are pluses. Plus, philic means to love. It's a plus lover. That's the translation for Greek, but it's not really its definition. That's just a straight translation, a dictionary translation. Plus lover. And look, it's loving that plus in bonding to it. But what its true definition is, it's a lone pair donor. It gives away that lone pair there to form a bond, and the lone pair will end up as a bonded pair in between the C and the O. It's a nucleophile, is a lone pair donor. And in doing so, in donating them and forming a new covalent bond here, the Br is lost or substituted, hence nucleophilic substitution. Next, we've got a big long passage here. I'm not going to read through it all because I need to pick things out. If I read through it all, we'll get confused. I need to pick the important bits out and go on this kind of scavenger hunt of a calculation. Let's have a look. What do we do first from all of this information? Density. Density is my key word. Density, I've been given a density. Why would I be given a density? The only reason I'd be given a density is because density equals mass over volume. So I've got to use density. I've got one equation that I can use. Density is mass over volume. So to work out the third thing, I need a second thing. Density, I've got mass. Have I got mass of the 1-bromo-2-methyl propane? No, I haven't, but I've got its volume. So I've got density and volume of 1-bromo-2-methyl propane. I must have density as mass over volume. I've got density, I've got volume, I must have to work out mass. So let's have a look at this calculation now. Density is mass over volume. What units are they in? Well, density is 1.26, that should be a 6 there rather than a 5, 1.26 grams per centimetre cubed. So that gives you a clue that the mass is in grams and the volume's in centimetre cubed. So that mass is in grams and the volume's in centimetre cubed. And I've got the volume in centimetre cubed, 2 centimetre cubed. So they're in the right units. 1.26 equals mass divided by 2 centimetres cubed. Mass is 1.25 or 6 times 2, so I've multiplied through by 2, 2.25 grams or there or thereabouts. Okay, so I've got the moles now. I can work out moles by looking at mass that I've got and dividing by MR. So moles equals mass divided by MR. I've got the MR of the 2-methyl propane, so that's the next step. 136.9. I've now got 0.0164 moles of 1-bromopropane. It's always useful to have moles because then I can refer back to my equation. I've got my equation. 1 mole of this makes 1 mole of this, and that's why I've got the equation here in front of me. So the equation tells me the molar quantities. After all, it's just a recipe with amounts in moles. 1 mole of this makes 1 mole of this. Have I got 1 mole of this? No, I've got 0.0164 moles of the 1-bromo-2-methyl propane. 1 mole would make 1 mole, so 0.0164 moles of this will make 0.0164 moles of my product, of my 2-methyl propan 1-ol. So now I know how many moles of 2-methyl propan 1-ol I've got. What other information have I got about the 2-methyl propan 1-ol? I've got its mass and I've got its MR. I could work out the mass theoretically, not using this value were obtained yet. I could work out theoretically how much I should make. I know that I should make 0.0164 moles. Moles is mass divided by MR. I've got the MR as 74. Moles is 0.164 equals mass divided by 74. Multiplied by 74. I should make 1.216 grams of my 2-methyl propan 1-ol. That's how much I should make. I've not used any experimental data yet. This is theoretical, just from maths and chemistry. That's how much I should make. Now it tells me how much I did actually were obtained, how much I actually did get. So I'm going to introduce this bit now, which is my actual yield. 895 milligrams. I've got a problem though because my theoretical mass is in grams, so let's turn milligrams into grams and then we've got comparable units. 895 milligrams, small unit into a bigger unit like grams, I'm going to divide by 1,000. So small unit into a larger one divided by 1,000, 895 milligrams divided by 1,000, 0.895 grams. That's how much I actually did make. So from all of my maths and my chemistry, it tells me I should make 1.216 grams. I've actually made 0.895 grams, so I've made less than I could have done, which is no surprise. Yield small number divided by a big number multiplied by 100, 73.6%. Let's check out why it's only to 3 significant figures. It's because that's to 3 significant figures, 895 is to 3 significant figures, 1.26 is to 3 significant figures, so 3 significant figures seems to be appropriate accuracy to use. 6.3. When 1-bromo-2-methylpropane reacts with hot concentrated ethanolic potassium hydroxide. Here's another clue. Hot ethanol. Ethanol, hot alcohol, hot ethanolic solution, hot ethanol. That means I get something called an elimination reaction. So when I change the conditions, I get an elimination reaction. Potassium hydroxide is the same as sodium hydroxide really in its reactive properties, so that doesn't really matter. I've got hydroxide, but I've got hot concentrated ethanol this time. And so the mechanism and the kind of reaction, what I make, changes. Potassium hydroxide rather than dilute sodium hydroxide doesn't really matter. That's a red herring. Doesn't really matter because the potassium and the sodium really are spectator ions. They don't do anything. It's the hydroxide that's important, as I mentioned before. Hydroxide OH-. If you include the sodium or the potassium in the mechanism, you'll get it wrong. I'm going to come back to those two again in a minute. I'm going to look at the mechanism. So the OH-, that's the important part. So when sodium hydroxide or potassium hydroxide dissociate, they make OH- ions, and there's a lone pair of electrons on the O, which is important. And the sodium and potassium are really not important. We don't include those at all. Now what happens in hot ethanol, hot ethanolic solution, is that you get a different mechanism. If you have a look at the CBr, instead of the OH- attacking the C here and replace the Br being replaced, what actually happens is you find the CBr, you go along another carbon, so you find the CBr along another carbon from that C and find an H. So you go from the Br 1, 2, 3 and you find an H. So you find the CBr, you find the neighbouring carbon, and you find the H on that carbon. And the OH- attacks that, bonds to that H. You use the lone pair of electrons from a curly arrow. Remember, it can't come from a minus, it's got to come from the lone pair of electrons. And it goes for attacks, bonds to the H. When the OH- and the H bond, that will actually make water. So HHO or H2O, and the minus is lost. There's no charge on the water because electrons are being given away. In other words, that H bonds to the OH- and makes water. Where do the electrons from the CH go? If the H is bonding to the OH, where do they go? They go between the two carbons here, between these two carbons, and will make a double bond. So those two electrons go into here to make an extra bond, a double bond between these two carbons, and the Br is always lost. In elimination and in nucleophilic substitution, the Br is always lost. It's withdrawing electrons towards itself anyway because it's electronegative, so the electrons move on to it. And you end up with an unsaturated product, something with a double bond in it, an alkene. Water, the Br- comes off, it gets the minus charge, so the minus charge balances and it's on the Br- because electrons are moved onto the Br. Why is it? What's the name of the product? Methylpropene. Let's have a look. 1, 2, 3 carbons, prop, ene double bond, and methyl group at carbon number 2. So you could call it 2-methylprop-1-ene. However, you can get away with calling it methylpropene because whichever end I label from, the methyl group is going to be at carbon number 2, and if I label from the right, it's the double bonds at carbon number 1. Or if it were this end, I just start labeling 1, 2, 3 from the other end. So the propene, the double bond, is always at carbon number 1. depending on which side you start labelling from. The methyl group's at number 2. So you can call it 2-methylprop-1-ene if you want to, but methylpropene suffices. Why is it called elimination? Because actually look at this molecule. It's got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and now it's only got 1, 2, 3, 4, 5, 6, 7. It's lost a hydrogen somewhere. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 there, and it's got 8 here. It's lost that hydrogen there, and it's also lost that Br there. It's lost atoms. Eliminate means to lose, to get rid of. It's had some of its atoms removed. That's why it's called elimination, and they come off here. Let's have a look at question 7, a difficult question here. We've got to fill in the rest of this mechanism. Let's have a look at this here. We've got a lone pair of electrons and an oxygen, and we've got an H+. There's a good chance that the arrow will go from the lone pair to the H+ and form a bond between the two. When it does so, we're going to make this, and the OH will bond between the O and the H, and make OH2. Where will the plus be? Well, the plus will be on the O, because that has had electrons move away from it, with the curly arrow going from the O to the H+. The H+ will lose the plus charge. Plus charge will be on the O, because electrons have moved onto the H and removed the H+ charge. So here, curly arrow to the H+, and the O gets the plus with an H2. What's next? Well, if you look at the next one here, forget that curly arrow, look at the next one that's given to you. It's got a plus charge on this carbon here, and this OH2 plus has gone. So how do we get rid of that OH2 and end up with a plus charge here? Well, this bond's got to break, and the electrons go onto that plus charge. It will release H2O then. The plus charge will disappear, release H2O, water, because the electrons have gone on to the O+, and so electrons being minus have eliminated that plus charge on there. This carbon now is short of the bond that was there. It's not got the bond that was there, so it's not got enough bonds. If it's not got enough bonds, it's got a plus charge on it. How does this then turn into this? Well, this H here that's been drawn for you has disappeared from here. It's gone, and so has the plus charge, and there's a double bond here. So clearly this H has got to break off, and which way will the electrons go? They'll go into here rather, and make the double bond. So they move from here to here. That will release the H as a H+. Make a double bond here, and then this carbon that hasn't got enough bonds has now got an extra bond and has got rid of the H+. Draw a structure of a different cyclic alkene formed from D. So formed from D, how could that work? Well, what could actually happen is, instead of this H breaking off here, why doesn't one of the H's here break off? So there's no reason why that H should break off from this carbon. We've got another carbon to the other side of the carbocation, the plus charge, here. So there's no reason why one of the H's here and H here couldn't break off. That H could stay, and one of these H's could break off and form a double bond here instead. So why is a H from here, from this carbon breaking off, why doesn't a H, instead of from there, why doesn't a H come from here and break off and form the double bond there? So the double bond could be here instead. (7.3) Let's have a look. Carbocation D can form a reaction called a rearrangement to form carbocation E. So this can turn into this. A hydrogen atom and its bonding pair of electrons move from A to carbon B as shown in figure 2. In other words, the plus charge moves. So why could the plus charge move? Why would the plus charge move? That's what the question's asking. So it's rearranged somehow. It's not asking you how it's rearranged, it's asking you why it's rearranged. Well, let's have a look at this plus charge here. this carbon here on this corner has got a carbon down here and a carbon here, a carbon either side of it. So this C plus, a carbocation, has got a carbon here to one side and a carbon here to the other side. This carbon with the plus, the carbocation, has got two carbons, one either side. It's a secondary carbocation. Secondary means that there's two carbons joined to the, bonded to the C with the plus. Whereas here, this carbon has got one carbon here, one carbon here, and one carbon here. It's got three carbons joined to the C with the plus. So the carbocation's got three other carbons joined to it. It's a tertiary carbocation. In other words, this is a secondary carbocation, this is a tertiary carbocation. The tertiary carbocation is more stable than the secondary carbocation, and that's why it's formed. So the question isn't asking how this rearrangement's happened, it's just simply asking you to recognise that this is a secondary carbocation, this is a tertiary carbocation, and the tertiary carbocation is more stable than the secondary carbocation, and that's why that happens. As a result of this rearrangement, a third alkene is formed from this reaction. Draw the structure of this third alkene. So what could actually happen is, from here, how does this plus disappear? How do we get rid of this plus? So what could actually happen is, this H could break off and go into a double bond between the two. Or the alternative is that one of these H's could break off and form a double bond here. So one of these three H's could break off and form a double bond here. That would get rid of that plus, because you'd have an extra bond. So this carbon now would have enough bonds, 4 bonds. At the moment it's only got 3 bonds. It would now have 4 bonds, so it would get rid of the plus. And one of the H's here would break off and release H plus and get the double bond in between the two here. And then finally, cyclohexene is prepared by the dehydration of cyclohexanol, concentrated phosphoric acid, which is there, cyclohexene, cyclohexanol, and phosphoric acid as a catalyst. So you're not asked for any kind of reaction, you're just asked to identify the boiling points of these three, and how cyclohexene can be separated from the reaction mixture. Well, this is phosphoric acid. I've drawn for you cyclohexene. So hex is 6, cyclo in a ring with an ene, a double bond, and cyclohexanol is 6 carbons in a ring with an OH in there as well. So you've got to identify which has got the largest boiling point. So the largest boiling point happens when you've got intermolecular hydrogen bonds. Oxygen joins to hydrogen, or fluorine joined to hydrogen, or nitrogen joined to hydrogen. So I've got 1, 2, 3 oxygen to hydrogen bonds. I'm going to have intermolecular hydrogen bond in between one of these phosphoric acid molecules and another. I'll get a very large delta plus delta minus polar bond on the OH, and that will form very, very strong dipole-dipole attractions with the other polar bonds in the other 3 OHs on a neighbouring phosphoric acid molecule, and those very, very strong dipole-dipole interattractions when you've got an oxygen joined to a hydrogen, a fluorine joined to a hydrogen, a nitrogen joined to a hydrogen. That's called hydrogen bonds. Very, very strong dipole-dipole. Plus the fact that we've got a phosphoric acid to an oxygen as well. This is going to be a polar bond, and so that's going to also form dipole-dipole attractions. This will have the highest boiling point because it's got hydrogen bonds in it, and it's got 3 OHs, so it'll have 3 sets of hydrogen bonds, and it's also got a polar bond here, the phosphorus to the oxygen, which will form dipole-dipole attractions. Next highest boiling point is this one, because it's got hydrogen bonds, but it's only got 1 OH, so it'll have 1 set of hydrogen bonds between the molecules. This one has only got carbons and hydrogens, so it's got no hydrogen bonds, it's got no polar bonds, it's going to have van der Waals bonds as intermolecular bonds, which are the weakest kind of intermolecular bonds between its molecules. So we've explained that. Explain how cyclohexene can be separated from the reaction mixture. So what you're going to use is distillation. You might use fractional distillation because you've got a mixture of 3 different liquids. So fractional distillation or distillation to separate liquids with different boiling points. Draw the skeletal formula of 3-methyl-butanal. So but is 4, so you're going to draw 1, 2, 3, 4 in a line, in a zigzag shape, 4 carbons in a line, so 4 lines. The butanal has got a C double bond O with an H on it. You don't need to draw the H, so you're just going to draw a double bond O. Butanal, the aldehyde group is always at carbon number 1, so you count along the chain and then put another branch off a line at number 3. Let's have a look how that looks. So let's go through it again. 4 in a line for but, 1, 2, 3, 4. This is your aldehyde group. It's the carbon there that's got a double bond O, and it'll have an H off it as well. So it's CH double bond O, a CHO group, CHO. You don't need to draw the H, we're leaving all the H's off. But one thing you need to recognise is that this aldehyde group is at the end of a chain, so that's always carbon number 1. So your methyl group's at carbon number 3. 1, 2, 3, and there's your methyl group. It can either go up or down, doesn't really matter. And that's your carbon, not showing its hydrogens, of the methyl group. Draw the displayed formula C5H11Br. That's the major product of the reaction of 2-methyl-butene with hydrogen bromide. So to show this, we need to do the mechanism and show you what it looks like. So here, this is your 2-methyl-butene. 2-methyl-butene. Let's just check. But 1, 2, 3, 4 in a line. 4 in a line. 1, 2, 3, 4 in a line. And at carbon number 2, if I start labelling this as carbon number 1, carbon number 2, I've got a methyl group and I've got a double bond at carbon number 2 as well. I could put this methyl group here instead if I wanted to. But I've got 4 in a line at carbon number 1, 2 at carbon number 2. I've got a double bond and I've got a methyl group. So that's 2-methyl-butene with hydrogen bromide. Now the HBr is going to join across here. The question is, the HBr, when the H joins on, does it join to this carbon or does it join to this carbon? Which way does the H join, this one or this one? Well, the rule is that a H bonds to the carbon that's already got the most H's bonded to it. This carbon's got one H bonded to it, this carbon has got no H's bonded to it. So the hydrogen will bond to this one, and that's to do with the stability of the carbocation that's formed. It's going to end up with a tertiary carbocation here. But just so that you can get it right, the H joins onto here, and the Br then will join onto the other one when Br minus with a lone pair. The lone pair is going to join onto the C plus that's there. So that's what it's going to look like. That gets you the marks. You don't need to draw this bit. This is what gets you the marks for recognising that this has got an H and this has got a Br in the product. Thermal cracking of hydrocarbons produces molecules that are attacked by electrophiles. Sorry, I've drawn the carbocation there. Once the H joins on the carbocation there, and the Br minus is going to join onto here. Draw the structure of one of these molecules that contains 4 carbon atoms. Let's read through it again. Thermal cracking of hydrocarbons produces molecules that are attacked by electrophiles. Electrophiles like HBRs, because they have a region of high electron density. Draw the structure of one of these molecules that contains 4 carbon atoms. High electron density means it's got a double bond. That's another way of saying that it's got a double bond. And electrophiles like HBRs will attack by electrophilic addition onto that double bond. So thermal cracking produces molecules 4 carbon atoms with a double bond. So 1, 2, 3, 4 carbon atoms with a double bond. The double bond can be here or it could be in the middle. Doesn't really matter. So it could be but1ene or but2ene. We've got chloroethene can be polymerized to form polychloroethene. So chloroethene is 2 carbons with a double bond, HH on one carbon, HCl on the other. and the double bond is broken to make single bonds either side, and they've all joined together, you can see the chloroethene that's been there as a monomer joined together as a series of repeating units. Chloroethene has a melting point of -154. PVC, this is polychloroethene here, the polymer, sometimes called PVC or polyvinyl chloride, melts at a temperature much over 100 degrees C. Explain why PVC melts at a higher temperature than chloroethene. Well, remember, chloroethene is a small molecule. Two carbons join with a double bond, HH on one carbon and HCl on the other, and it's only when they form a polymer that they join together to make a large molecule. So there's one mark for saying it makes a large molecule, and then a large molecule is going to have more atoms, more electrons, more stronger van der Waals forces between the molecules. So one mark for saying the molecules are larger in polychloroethene or PVC, and that there are stronger van der Waals forces between the molecules in the PVC polymer, so the melting point's higher. The structure shows that a molecule that's been used in PVC reduced the number of hydrogen atoms in the molecule. So what you've got to do is you've got to recognise every carbon's on a corner. There's carbons on each of these corners, and the H's, the hydrogen atoms, have been left off. But every carbon has 4 bonds. So what you've got to do is you've got to go through and make sure that there's 4 bonds off every carbon. Some will need none. Say, for example, that's already got 4 bonds. That's got 3, so that'll need an additional 1. That's got 4 bonds. That's not a carbon. This carbon here has got 2 bonds, so needs 2 more. This carbon at the end needs 3 more. And when you draw them on, it will look a little bit like that. I've drawn the red bonds to each of the H's. You count them up and there are 38 hydrogens that are needed to make sure every carbon has got 4 bonds. Use your understanding of the properties of PVC to explain whether you'd expect to find a plasticizer in PVC to insulate electrical cables. What a plasticizer does is it gets between the PVC molecules. So it gets in between the molecules and prevents the van der Waals bonds, or at least weakens the van der Waals bonds between the molecules. So what it does is it makes it more flexible, it makes it bendy. So would you expect that plasticizers to be used in insulated electrical cables? Yes, plasticizers are used to soft molecules. The plasticizer is present in the plastic insulation to make it bendy. So that's your answer. A section of polymer, the polymer polychloroprene, synthetic rubber, is shown below. So I've got carbons at each of these points here. I've got a double bond and I've got some Cl's. You need to recognize the repeating unit. Well, if I take this bit here down to a Cl, the next time it appears is here. And the next time it appears is here. So the cut-off point is here. So I can see there's a repeating unit going from here round here, and there's a repeating unit going from here round to here to this point here, and then there's a repeating unit going round to here. So I've recognised the 3 repeating units. So now I just need to draw one of them. So I've got a carbon to Cl, carbon to Cl, a double bond to a carbon to a carbon to a carbon. So I've drawn that section there, and I've drawn the displayed formula. So rather than skeletal, I've drawn displayed with all of the bonds and the H's showing. It's important, it mentions here you need the displayed formula for the repeating unit, so it's important to draw all the bonds in. Question 10. Trickier question you think here because you're reading from a burette. Look, the numbers are going down. 22, 23, 24, 25. And you've got to work out each graduation then is 0.1. You've also got to work out that it's the bottom of the meniscus that you read from, not the top. So we go 24, 24.1, 24.2, 24.3. 24.3 is the bottom of the meniscus reading down in 0.1. 24.3 is answer B. Question number 11. So I've weighed out some solute. Solute is just a general term for something that dissolves in something. So the solutes start off with, after the weighing bottle is 4.48, that's the mass of the bottle, that's the mass of the bottle plus the solute, the solid that you're dissolving in the liquid. So if I subtract the two, then I'll find out the mass of the solute. Once I've found the mass of the solute, I need to work out the uncertainty. Now I've got two readings. I've got a reading of a mass with the solute, and then I've got another reading of just the bottle on its own afterwards, after I've added the solute, poured the solute from the bottle. So I've got two readings. Each reading, read this carefully, each reading from the balance has an uncertainty of 0.005, but I've read from the balance twice. So I've got that uncertainty the first time I've read, and that uncertainty the second time I've read, so my uncertainty is twice. Let's have a look at that solution. The mass used 10.13, take away 4.48, 5.65 grams I've added. The balance each time it's used has got an uncertainty of 0.005, and I'm doing two readings on the balance, so I've got to multiply that by 2. So the total uncertainty is 0.005 times 2, which is 0.01. The uncertainty is the small number divided by the big number, 0.01 divided by 5.65 multiplied by 100%, 0.18. The answer is C. Which of these is going to produce this spectrum? Now let's go through. We've got a data book alongside us, but let's see if we can do it without the data book. Ethanol. Ethanol has got an OH, and OH produces a broad, large absorption here, around about 3,500, and that's not there. So it's not ethanol, because the OH, the alcohol, would produce a broad, wide absorption around about 3,500. Propanoic acid has also got an OH, and its OH is also wide and broad, sort of here around about the 3,000 mark, 2,500 to 3,000, somewhere here, and that's not present, that's not broad and wide. So anything with an OH, an alcohol, or an oic acid, an OH is a broad, wide absorption, so it's not B and it's not D. Pent-2ene, the carbon-to-carbon double bond, is going to be quite hard to spot. Butanone, the carbon-to-oxygen double bond, is here. That's that one at around about 1,700. Let's have a look at the data book. Butanone, carbon-to-oxygen, is present 1,680 to 1,750. That's that one, as we've said. So we've identified a carbon to oxygen double bond. Ethanol hasn't got a carbon to oxygen double bond and hasn't got the broad, large absorption that's at 3,230 to 3,550. Pentanene is a carbon to carbon double bond. That should be at 1,620 to 1,680, around about here. Sometimes quite difficult to spot around about here, but we know it's not pent-2ene anyway, because we've identified this carbon to oxygen double bond, which is a really strong peak, absorption peak here at 1,680 to 1,750, and propanoic acid OH would be a broad, large absorption here around about 3,000, 2,500 to 3,000, so it's definitely butanone. What's the most likely bond angle of the oxygen atom in ethanol? Well, let's consider ethanol. Ethanol has got a C with an O to an H, so it's got COH. Oxygen's in group 6, so it's got 6 electrons in its outer shell. It will use one of those electrons to form a pair, to form a covalent bond with the carbon, and it'll form and use another electron to bond to the hydrogen. So it's got one electron of its 6 used to bond to the carbon, one electron of its 6 to bond to the hydrogen. It's got 4 left. It's going to have 2 lone pairs. So if it's got 2 lone pairs, if it's got 6 in its outer shell, it's going to have one of its electrons in the shared pair with the carbon, one of its electrons in the shared pair with the hydrogen, and it's going to have 4 left. 1, 2, 3, 4. It's going to have 2 lone pairs. So it's got 2 bonded pairs and 2 lone pairs. The way you work that out is 4 bonding pairs has got a bond angle of 109.5 and is tetrahedral. If you introduce 1 lone pair, then that value comes down by 2.5 to 107. So if you've got 3 bonding pairs and 1 lone pair, it comes down to 107. 2 lone pairs and 2 bonding pairs comes down by another 2.5 degrees to 104.5. So that would be V-shaped, 104.5. Which compound is a structural isomer of Z-butene? This is testing that you know what the difference between structural isomers, which have got the same molecular formula but a different structural formula, such things as chain isomers, position isomers and functional group isomers, and that you're not confused by the red herring of the Z. The Z is a stereoisomer where you've got the same structural formula but a different position of atoms in space, usually because you've got no free rotation about a double bond, and so you get Z and E. But that's stereoisomerism or geometrical isomerism, and it's asking for structural. So it wants to know a structural isomer of this, either a chain isomer, where you're changing the length of the chain from bute, which is 4, down to 3, or whether you're using positional, changing the position of the ene from a 2 to a 1, or whether you've changed the functional group and got rid of the ene altogether. So let's have a look. Butane. Well, butane is not going to be an isomer because it's going to have the molecular formula C4H10. Butene has got the formula C4H8, CN2N. So this butane has got too many hydrogens. It's not got the same molecular formula. It's not even an isomer. E-butene, we've mentioned Z and E. Yes, they are isomers, but they're geometric isomers or stereoisomers where you've got no free rotation about the double bond, and therefore you've changed the two methyl groups. One is up and one is down on the E. They're opposite to each other. Z are on the same side of the double bond. Yeah, they're isomers, but they're not structural isomers. They're geometric or stereoisomers. Cyclobutane looks good. Let's just check out D. Methylbutene. Well, butene has got 4 carbons, and a methyl group has got a carbon in it as well. You've just introduced 5 carbons into that. This has only got 4. You've changed the molecular formula, so it can't be that. You've added another carbon to it. Not allowed. Cyclobutane, cyclobutane rather. Bute 4 carbons. Yes. Cyclo means that it's in a ring, and therefore it can have 8 hydrogens, just as butene has 8 hydrogens as well, and you've got rid of the ene, it's become an ane. This is a structural isomer, it's a functional group isomer of Z-butene. Your answer is C. Question 15 and 16. Which equation is a propagation step in the conversion of trichloromethane into tetrachloromethane by reaction with chlorine in the presence of ultraviolet light? So if you've got chlorine in the presence of ultraviolet light, you've got free radicals. You've got atoms or groups of atoms with a dot, an unpaired electron on there. So A is definitely not it, because that's not even a free radical reaction, so it's not A. So you're looking for reactions with dots in them, so it could be B, C or D, but it's definitely not A. If you have an initiation step is where the dots only appear on the right, so you've got something like chlorine Cl2 making 2 Cl dots on the right. So we haven't got anything like Cl2 going to 2 Cl dots. We've got no initiation step. Okay, we're after a propagation step anyway. A termination step is where 2 free radicals come together, 2 dots, to make something without dots. So that's a termination step, B. 2 dots coming together to make something without dots, 2 radicals coming together and joining together and forming something with covalent bonds without dots, with no unpaired electrons. They're all involved in covalent bonds, shared pairs. So it's not B, so it's not A and it's not B. So we're between C and D. Which one looks possible? So a propagation step, you never find an H on its own, an H with a dot, so I'm never going to find that. I'm never going to produce that. If I had those two coming together, then the Cl dot would react with an H and make HCl and a CCl3 dot. So a Cl dot always makes a HCl, never a H dot. So it's definitely not C, so it's got to be D. it has to be D, and that looks correct. So I've got CCl3 dot reacting with more chlorine to make CCl4. It says it's making trichloromethane into tetrachloromethane. There's tetrachloromethane, and it's making a Cl dot, so it's reforming the radical, the chlorine radical, which is part of the reaction anyway, to reform the Cl dot as a catalyst. Your answer is D. Which compound has the fastest rate with potassium cyanide to form pentane nitrile? So which one of these will react with potassium cyanide? A cyanide ion is a Cn- with a lone pair on it. It attacks the carbon bonds to a carbon, and then either the Br, the Cl, the F, or the iodo release then, so the bond breaks. So as the Cn- ion and the lone pair bonds to the C, then you need the Br, Cl, F or I bond to break, the electrons to move from the bond onto the Br, Cl, F or I and make a Br minus ion, a Cl minus ion, an F minus ion or an I minus ion. Which one will go the fastest? It's the one with the weakest bond. The one with the weakest bond is the largest atom because the shared pair of electrons are not held as tightly. So the iodobutane has got the weakest, largest. Iodoiodine is the atom at the bottom of group 7, the larger atom, and so that's going to have the weakest bond. Question 17. Which alcohol can be oxidized by acidified potassium dichromate? So that's orange, and it will go to green, and it will oxidize primary and secondary alcohols. It won't oxidize tertiary alcohols, but cannot be dehydrated by heating with concentrated sulfuric acid. So let's first of all get rid of any tertiary alcohols because they won't be oxidized by potassium dichromate. A tertiary alcohol is where the C with the OH has 3 other carbons bonded to it. So the C with the OH has 3 other carbons bonded to it. Let's have a look at this. Butan-2-ol. So the OH is at carbon number 2. So it's in the middle of a chain at carbon number 2. It's got carbon number 1 and carbon number 3 around it. Is there a methyl group at carbon number 2? Yes, there is. There's 2 methyl groups, one at carbon number 2 and carbon number 3. So on carbon number 2, it's got a carbon on carbon number 1 and a carbon alongside it to the right on carbon number 3, and it's got a methyl group at number 2. That OH is surrounded by 3 carbons. That's a tertiary alcohol. It's not going to be oxidized by acidified potassium dichromate, so we can rule out A. Let's have a look at C. 2-methylpropan-2-ol. 3 carbons in a line. The OH is in the middle of the 3 carbons at carbon number 2. So it's got carbon number 1 and carbon number 3 either side of it. Oh, and at carbon number 2 it's got a methyl group as well. So that carbon number 2 has got the OH, it's got a methyl group, and it's got a carbon either side of it, 1 and 3. So the C with the OH at carbon number 2 has got 3 other carbons around it. That's a tertiary alcohol as well. So A and 3 are not going to react with acidified potassium dichromate. Propan-1-ol, so you've got carbon number 1, you've got the OH, and you've got methyls at carbon number 2. That looks as if that's a primary alcohol. Pentan-3-ol, 5 carbons, and the OH is in the middle at carbon number 3, but it would have 2 carbons either side at carbon number 2 and 4, and an H off carbon number 3. That would be a secondary alcohol. So B and C could be oxidized by acidified potassium dichromate, the primary alcohol and the secondary alcohol. The question is, which one wouldn't be dehydrated with concentrated sulfuric acid? So what you need for the concentrated sulfuric acid, what it does is it takes the concentrated sulfuric acid, removes water. It removes water and dehydrates something, removes water by removing an OH from one carbon and removing an H from the neighbouring carbon. So you need an H on a carbon, and on the neighbouring carbon you need an OH. So presumably one of them hasn't got an H on the neighbouring carbon. Let's have a look. Propan-1-ol, so the OH is on carbon number 1, and on carbon number 2, you've got 2 methyl groups, and you'll have a carbon number 3 as well joined to it. So that carbon number 2 has got 2 methyl groups, and it's got carbon number 3 joined to it as well. So that carbon number 2 there hasn't got an H joined to it. So it's not got an H on carbon number 2 that can be removed along with the OH on carbon number 1. B cannot be dehydrated with concentrated sulfuric acid, so that must be your answer, answer B. Let's just check out D. D has got an OH at carbon number 3, and at carbon number 2 or at carbon number 4 it must have an H, so that will have an H at carbon number 2 and no H at carbon number 3. We'll also have an OH at carbon number 4 and no H at carbon number 3. Yes, it's got an H and no H on neighbouring carbons. That would be dehydrated. Your answer is B. How many structural isomers there are there with the molecular formula C3H4BrCl? So I'm just going to do spoilers on this so we can see it a little bit better. C3H6BrCl. So you've got 3 carbons in a line, you've got 6 H's, and you've got a Br and a Cl. So the question is, where can the Br and the Cl's go? What combinations can we have? So at carbon number 1 we can have a C, and we can have the Br also at carbon number 1. So both the Br and the Cl at carbon number 1, and the H's then are just on the other carbons. We could have a Cl at carbon number 1, a Br at number 2. We could have a Cl at carbon number 1, a Br at carbon number 3. I think that's all the combinations with a Cl at carbon number 1. With a Br at carbon number 1, also carbon number 2 or carbon number 3. Therefore, the next combination is a Cl at carbon number 2. Well, you could have a Br also on the same carbon, or you could have a Br at carbon number 1. Remember, if the Cl is at carbon number 2, then carbon number 1 and 3 either side are effectively the same, depending on which end you label them at. So say for example, if you have a Cl at carbon number 2, then the Br at carbon number 1 is the same as at carbon number 3. And similarly, if you have a Cl at carbon number 3, that's the same as at carbon number 1. So your answer is B, 5 different combinations. Question 19 and question 20 both involve some calculations, so I'm going to do spoilers so you can see my calculations. So first of all, I've got some information here, Avogadro's constant, which is the number of particles in 1 mole, and I'm going to work out how many moles of each of these there are. So in number A, 6.022 times 10 to the power 23 are the number of particles in 1 mole. I've got the number of particles here, which seems to be less than this number, 2.10 times 10 to the power of 22 only, not times 10 to the power of 23, so I've got less than a mole. So let's work out the fraction of a mole that I've got. So I'll take the smaller number, 2.1 times 10 to the power of 23, divide by the larger number, and I'll work out the fraction of a mole that I've got. I've got 0.0349 moles in A. 1 gram of oxygen, well, O2 has got 2 O atoms, each with a mass of 16, so it's got an MR of 32. I've got 1 gram of it, so moles is mass divided by MR, 1 divided by 32, I've got 0.03125 moles of gas in B. In C, I've got milligrams of hydrogen. Well, I can do the same thing, milligrams into grams. If I'm going from a small unit like milligrams into a large unit like grams, then I divide by 1,000. 65 divided by 1,000 is 0.065, so that's the mass in grams. Moles is the mass in grams, 0.065 divided by its MR. Hydrogen, there are 2 H's, each with a mass of 1, so that's an MR of 2, 0.0325 moles. And the last one, it just tells me the number of moles. So all I've now got to work out is which one contains the most molecules. So there's a certain amount of molecules in a mole, so that's the same thing. I'm working out how many moles I've got. They'll all have the same. 1 mole of anything has 6.022 times 10 to the power 23 molecules. So in other words, I'm just working out which one has the largest number of moles. Which one has the largest number of moles? The answer is A, 0.0349, which is bigger than any of the other values. So that one will have the largest number of molecules. Which compound forms a molecular ion with a different precise molecular mass from the other 3? Well, what you do is, in a mass spectrometer, you take the ion, you take the atom, you take the particle and you remove an electron from it with something called an electron gun, and then that forms a molecular ion. In other words, it's the molecule that's got a plus charge on it. It's had an electron removed from it. And what you then do is you can measure the mass of that ion. So in other words, it's saying if each of these were made into plus ions and the mass of each of these ions then of these molecules were measured in a mass spectrometer, which would be the largest. So what you've got to do first of all is you've got to work out the MR. So in other words, which one of these has got the largest MR? That's what the question's asking. Make these into plus charged molecules, put them into a mass spectrometer, measure the mass of the molecules, which one has got the highest MR. So if I work out the formula, the molecular formula of each of them, C4H8O, C4H8O, C5H12O and C4H8O, they're all got 4 carbons, 8 hydrogens and 1 oxygen, apart from C, that's got a different relative formula mass, a different molecular formula. So this one would have a different relative molecular mass when you measured the mass of the molecular ion in the mass spectrometer. Your answer is C. Question 21 and 22 both involve calculations, so I'm going to do reveals so I can talk you through the calculations. So first of all, in an experiment, 4.2 moles of carbon monoxide, so that's that, were mixed with 2 moles of steam, and then we haven't got any carbon dioxide and any water, any hydrogen at this point. So I've got 4.2 moles of that, 2 moles of water, no carbon dioxide, no hydrogen. Look, it's a reversible reaction, so it can go in the forward direction and the backward direction. And then when dynamic equilibrium's reached, which is where the rate of the forward and backward reactions are the same and the concentrations of the reactants and the products are no longer changing anymore, then the concentrations of these will stay the same. Let's work out how many moles of products we've got. We've got at equilibrium, we've got 1.6 moles of hydrogen made. Now if you look, 1 mole of this and 1 mole of this react to make 1 mole of this and 1 mole of this. So I've just made 1.6 moles of hydrogen. I must at the same time make an equal amount 1:1 of carbon dioxide. I make 1.6 of this. How much carbon monoxide is used to make 1.6 moles of hydrogen? And the answer is 1.6. So 1.6 carbon monoxide is used up to make 1.6 moles of hydrogen, because it's 1:1 to 1:1. And similarly, 1.6 moles of water is used up. So if I subtract that and work out what I've got at the end, 4.2 moles of carbon monoxide, 1.6 used up, I've got 2.6 remaining. 2 moles of water to start with, 1.6 used up, I've got 0.4 remaining. I've made 1.6 of carbon dioxide, 1.6 of hydrogen. Now my Kc is the concentration of carbon dioxide divided by, multiplied by the concentration of hydrogen, divided by the concentration of carbon monoxide and divided by the concentration of water. Now concentration is number of moles divided by volume, and we haven't got the volume of the container. But the reason we've not got the volume container, it doesn't matter. We've got equal numbers of moles, 2 moles on the left-hand side and 2 moles on the right-hand side. And when you've got equal numbers of moles on each side, on the left-hand side and on the right-hand side, the volume of the container really doesn't matter when we're working out Kc. Because if I divide each of them by the volume to get the concentration, all of the volumes cancel out. So moles become concentrations for the purpose of working out Kc. 1.6 times 1.6 divided by 2.6 times 0.04. I'd work those out individually. If you're doing a calculator, work that out and then work that out, and you'll find out it's 2.56 divided by 1.04. 2.46 is your answer. The answer is D. Let's have a look at 22 then. Let's talk through this. A sample of 2.0 moles per decimeter cubed acid, so I've got a concentration as a volume. So first of all, I know I've got to work out moles, because concentration is moles divided by volume. The problem is that needs to be in decimeter cubed, because here I've got concentration with the units decimeter cubed. This needs to go into decimeter cubed. Small centimeter cubed into decimeter cubed. Small units into larger units are divided by 1,000, so 100 divided by 1,000 is 0.1. So now my concentration is moles divided by volume. Concentration 2 equals number of moles divided by volume, 0.1 decimeter cubed. I've worked out then moles is 2 times 0.1. I've got 0.2 moles of a sample, and I knew that I needed to work out moles because I've been given concentration and volume, so it's directed me in that way. What volume and water should be added to this acid to dilute the sample to a concentration of 1.5 mole per decimeter cubed? Well, the number of moles of acid hasn't changed. All I've done is put it in a flask and added some more water. So the number of moles of acid hasn't changed. I've just added some water. So my number of moles of acid is the same. So my moles of acid is the same. I know my concentration. So I know concentration, I know moles. I know concentration is moles divided by volume. My concentration is 1.5 because it tells me it there. My moles of acid haven't changed. I've only added some water divided by the volume of the flask, the volume of the liquid rather. So 1.5 equals 0.2 divided by the volume of the liquid. So I could say volume equals 0.2 divided by 1.5, 0.1333 recurring decimeter cubed. It's in decimeter cubed because units of concentration are decimeter cubed. So I could convert that into centimeter cubed because all of these answers are required in centimeter cubed. How do I convert decimeter cubed into a smaller unit like centimeter cubed? I multiply by 1000. 0.1333 recurring times by 1000 is 133.3. So that's my final volume. So is 133.3 on there? No. Okay, and the reason that 133.3 is not on there is so sometimes they would do that to try and fool you into that as the answer, but read the question carefully. What volume of water should be added to the acid? So the final volume is 133.3. We've started with 100 centimeter cubed of acid, so you've got to add 33.3 centimeters cubed of water. Your answer is B. Questions 23 and 24 both involve some calculations, so I'll do spoilers and then talk you through the answers. So in here it looks as if I've got some flasks, I've got some moles, I've got some masses, but this is the key thing. It says the temperature and the pressure are the same. So I need to use PV equals nRT because that's got temperature and pressure in it. And actually when I look, the pressure and the volume are staying the same because it's a seal flask, same volume, same pressure, same temperature, and R is the gas constant, 8.31. So everything is staying the same. So flask A contains this number of moles of methane. So PV equals nRT if I work it out for this one, and all of these are going to stay the same. When I work out n number of moles, it equals that. When I work out this, n number of moles with the same pressure, the same volume, the same R and the same T, n must be the same for this as well. So if PV and R and T are the same in this one and the same in this one, then this other number, n, must be the same in both of them. So in other words, all this information is saying that flask A and flask B have got the same number of moles of gas. So 4.0 times 10 to the minus 3 moles of methane, this flask B must contain 4.0 times 10 to the minus 3 moles of methane as well, because n number of moles must be the same for both of them, because everything else is the same. So when you work out n, it must be the same. So flask B has got 4 times 10 to the minus 3 or 0.004 moles of gas as well. We've been given a mass in milligrams. To turn a small unit in milligram into a large unit like a gram, then we divide by 1000. So 340 milligrams is 0.34 grams. Moles is mass divided by mR. So moles, which is 0.04, we've established that, 0.004 rather, equals number of mass, 0.34 divided by mR. It's prompting us from the mass and the number of moles to work out mR. mR is 0.34 divided by 0.04. The mR is 85. In other words, it's saying which of these chemicals has got an mR of 85. Well, let's go through them. A, CH2Cl2. A carbon is a 12, hydrogen's a 1, Cl's a 35.5. You add it and you've got 85. You could check the others, but I've found it straight away. It's answer A. Analysis of sample of a chemical C22H33N5O4S showed that it contained 0.0195 moles of carbon. So what do these numbers tell you? They're the ratios of the number of atoms or the number of moles. It's the ratio of number of moles. So if I had 22 moles of carbon, I'd have 5 moles of nitrogen in there. So I've got less moles of nitrogen than I have of carbon. 22 carbon for every 5 nitrogen. So to work out the number of moles of nitrogen, I could multiply 0.195 by 5 and divide by 22. If you can't see that, another way of looking at it is that the ratio of moles of carbon to nitrogen is 22 to 6, so it's a 6, not a 5. I divide both by 22, so the ratio of carbon 1 to nitrogen 6 divided by 22 is 1 carbon for every 0.273 moles of nitrogen. So my moles of carbon is 0.195 multiplied by 0.273, 0.0053 moles of nitrogen. So I have got 0.0053 moles of nitrogen. If your maths is good, the quicker way of doing that would have been, as I say, to say 22 carbon for every 6 moles of nitrogen, a lot less nitrogen than carbon. What's the fraction of nitrogen compared to carbon? 6 divided by 22 multiplied by the 0.195, and it gives you 0.0053. Any way that you can work that out. Now then, I've got the number of moles of nitrogen in there. What's it asking me? What mass? Well, I know moles is mass divided by mR. Moles, I've got 0.0053. Mass, mR of nitrogen I know is a 14 from the periodic table. 0.0053 is mass divided by 14, so the mass is 0.0053 times 14, 0.074. So my answer is C.